There are 5 forms of nuclear radiations: alpha, beta, gamma, positron, and neutron. Alpha radiation is going to have the helium nucleus. So remember, helium has a mass number of 4 and atomic number of 2. So the charge is 2 plus and the mass number is 4. And beta radiation is going to be similar to that of an electron, where the charge is going to be 1 minus. And remember, the electrons doesn't have any mass, or the mass is negligible, and therefore it's going to be 0. And gamma radiation has 0 charge and 0 mass number. Positron is going to have plus 1 and mass number is 0, and neutron is going to have a charge of 0 and mass number 1. Okay, so I want you guys to definitely look into the symbols and kind of memorize it, okay, because we need that for writing down the nuclear decay equations. Okay, so let's go ahead and do some problems here. I'm going to give you guys some examples for nuclear decay equations. Okay, the first example that we have here is alpha decay. So when thorium-232 90 undergoes alpha decay, it's going to give off alpha radiation, which is basically the helium nucleus. Okay, and you needed to predict like what's the atom, what's the nucleus that will be liberated during this reaction. Okay, so remember, a nuclear decay reaction is conversion of one nucleus into another nucleus. Okay, you needed to find like what is this X. Okay, the most important thing in here is, in a nuclear decay equation, the sums of the mass numbers and the sums of the atomic numbers will be equivalent on each side. So just as you balance a chemical equation, the normal chemical equation, the everything on the left side for the mass numbers and the atomic numbers should match up with everything on the right side. Okay, so we know that helium nucleus is actually liberated out. So this number right here would be 232 minus 4, and this would be 90 minus 2. Okay, so the value for 90 minus 2 is actually 88, and 232 minus 4 would be 228. Okay, and then once you figure out like the mass number and the atomic number of this particular atom X, you need to go to the periodic table and find where is this atom 88 coming. Okay, so atom 88 is nothing but radium, okay, which is right here. Okay, so which has a symbol Ra, and you replace the X with Ra. So the balanced equation right here would be 228 Ra 88. So this is the balanced equation. Okay, I think we should also be you should be able to do the beta decay now. Okay, remember, you have to memorize the symbols. Okay, otherwise it's hard to do. Okay, and let's say that you have carbon 14 with atomic number 6, and you want to do the beta decay for this. And remember, the beta decay is going to have the emission of an electron. Electron has a charge of -1, right? And you wanted to find out what is this X. Remember, X is going to be 14 minus 0, and then 6 minus -1. Okay, so the value for this is going to be, if I want to write the X here, so that's going to be having a mass number of 14, and then 6 minus of -1 equals 7. And now what is this atom 7? What is this atom which has an atomic number of 7? So you're going to find, so here is the periodic table, and you're going to find the atom which has number 7, atomic number of number 7. So that would be nitrogen. So you replace the X with nitrogen, and you put that in the equation. Okay, so that would be nitrogen 14 7. So this would be the complete equation for beta decay. Now the last one is the gamma decay. Let's see what's going to happen when lead, which is represented by Pb, is undergoing a nuclear decay reaction where gamma radiation is emitted. Okay, so here is the gamma radiation. So the meaning for this asterisk symbol right here is actually to symbolize an atom which is going to have higher energy. So during this process, there is going to be gamma radiation that is emitted. So remember, gamma radiation doesn't have any charge and doesn't have any mass. Okay, so it's going to be 0 and 0. So this X will have mass number of 204 because basically you're subtracting 0 from 204 and subtracting 0 from 82. So that will be just 82. And again, you don't have to even look into the periodic table to find what X is because X is nothing but Pb. So you'll replace the X with Pb. Okay, I hope this is clear. There are a few examples on the PowerPoint. I wanted you guys to definitely go through each and every single problem up there, because those are going to help you in the exams. And I really want you guys to understand this concept. Okay, so let's see whether you can do this one. So uranium-238 undergoes alpha decay. For sure, alpha decay is going to give off helium nucleus, right? And you're going to replace this with, you're going to put an X there. And to find the mass number of this X, you're going to subtract 4 from 238 and 2 from 92. So that's going to give 234. And 92 minus 2 would be 0. Sorry, 90. And I don't know this X. I will still have this alpha particle. Okay, and I go to the periodic table and find what is 90. Okay, so 90 is right there, which is thorium, which has a symbol TH. So now I will replace the X with the symbol of the atom, which is TH. Okay. Okay, the next one is the half-life of a radionuclide. Half-life is the time it takes for half of the nuclei of a given sample to decay. Okay, in other words, after one half-life has expired, only one half of the original amount of nuclei is going to remain undecayed. After two half-lives, only 1/4 of the original amount of the radionuclide remains undecayed. So to explain this, we have this little diagram here. Let's say that you have a radioactive element, radioactive nucleus, which is thorium-234, okay, which has a half-life of 24 days. Okay, so at day 0, you have about 100 grams of uranium or thorium-234. After the first half-life, okay, so what happens is, like, after 24 days has passed, you will have 50 grams of 234 thorium. And then after the second half-life, which is another 24 days, you will have 25 grams of thorium. Okay, so now you should be able to predict like how many grams will be left after the next 24 days. Okay, so here is the decay curve for any radionuclide. So as you can see, as the days go, the radioactive nuclei, the amount of the radioactive nuclei is actually decreasing, but it is not going to go to 0 at all. It's going to take infinite days for it to decompose completely. Okay, here are the half-lives of some radionuclides. So when you take beryllium, it's actually very less, which is equivalent to 6.7 times 10 to the power of minus 5 seconds. And but when you take carbon, it's actually 5,730 years. But look at this. Uranium 238 is actually 4.46 times 10 to the power of 9 years. That's a long time for it to decay. And indium 115 is even longer. It's actually 4.4 times 10 to the power of 14 years. So okay, now how do we actually determine the half-life of a radioactive isotope? It is through Geiger counter. There is a machine called as Geiger counter. It is with that we'll always measure the half-life of the radioactive isotope, and this is how it looks like. But I'm not going to go into the details of it. Probably I'll post a video for you guys to see. Okay, so the next one is a radiocarbon dating. Because of the constant decay rates, radioisotopes can be used as nuclear clocks. Scientists can determine the age of objects that contain radioisotopes. So one of the advantage of the radio isotopes is the dating procedure that can be useful in archaeology. So this is used on materials that were once part of living things, wood, bones, parchment, etc. So say for example, if you take carbon 14, it is actually formed naturally in the upper atmosphere and is dispersed by atmospheric mixing. All living matter contains about the same level of 14C. But then like when they die, it ceases to take in carbon 14, and the carbon 14 present at death starts to undergo radioactive decay. Therefore, the longer an organism has been dead, the lower is the radioactivity of each gram of carbon in its remains. So, there is also a video that I've posted. I want you guys to definitely listen to it.